Okay, so the next step is to do the whole question again, but for total correctness. And thankfully we can recycle a lot of our previous answer. We don't have to find an invariant, and we don't have to do this part of the tedious proof onwards, because it's exactly the same for total correctness. We just need to do this part. Once we get to the while, you're done, right? You do the same things before. It's getting up to the while that has to change. So we need to find a variant, E, such that these two conditions hold. So if we have a look at our little table of numbers from before, we want to identify something that's non-negative while the code is running, and strictly steps down each loop iteration. So once again, because I is ticking up, it seems like n take I is probably going to be a good choice for the variant, because n take I is going to tick down as I ticks up. So we're going to let E be equal to n take I, just like we did last time. This is, finding the variant is usually pretty easy, because you sort of identify the thing that's ticking up. Well, if there's something ticking down, you just use that. And if it's not something ticking down, there's probably something ticking up, and then you can use that to make something that ticks down. Okay? So we'll just roll with that for our variant and check that it works. I promise you it will. So now we've got two things to show. We have to show that P and B implies E is greater than 0, and we have to show this great big rule here. So what was our variant? N take I. Okay, so we better check rule 1. If P is true, so what's the statement? That's not right. P is the statement that S is equal to I. That's better. Okay, so we need to show that S equals I plus 1 on 2, and I less than or equal to n, and I strictly less than n implies E, which is n take I, is greater than or equal to 0. And that's not hard to show, because you can just take this term here and rearrange it to obtain this term here. So that trivially works, so that was an easy one. The tricky part is proving this part here. So that's the majority of the proof, so let's go through it. We need to show that P, namely S equals I plus 1 on 2, and I less than or equal to n, that's my P, and B, so and I strictly less than n, and E is equal to m, so n take I is equal to m. Okay, so I'll just color code this for you. This part here is P, this part here is B, and this part here is E is equal to m. Okay, we then put our code, so increase I by 1, increase S by I. Okay, and our post condition is P, which is again this thing. So I'll do it in a different color, why not? So S is equal to I plus 1. I should do it in red, so the red matches the red over there. S equals I times I plus 1 on 2. And I is less than or equal to n. And we require that E is strictly less than m, so E got slightly smaller. N take I is strictly less than m. Okay? This is the thing we have to prove. There's no more while rules kicking around in here. We only got regular Hall logic rules, so we're going to have to do sequencing. So do sequencing backwards. S equals I plus 1 on 2, and I less than or equal to n, and I strictly less than n, and n take I is equal to m, first bit of code, and then blah, some q, and then blah, the same q, S is increased by I, and post condition, all this stuff. S is equal to I plus 1 on 2, and I is less than or equal to n, and n take I strictly less than m. Alright? Yada yada yada, do assignment backwards. Didn't even do it right. S plus I equals I plus 1 on 2, and I less than or equal to n, and n take I strictly less than m. Copy the same, so this is true by assignment. copy the same condition across. S plus I equals I plus 1 on 2, and I less than or equal to n, and n take I strict less than m. Getting some serious deja vu here. Is this a valid form of the assignment rule? No, it's not. Do assignment backwards on the post condition. S plus I equals I plus 1 on 2, and I less than or equal to n, and n take I strictly less than m. I is assigned to be I plus 1. And we have something yucky on this side. We're going to have replacing all the i's with I plus 1's. S plus I plus 1 is equal to I plus 1, I plus 1 plus 1, all on 2. And I plus 1 is less than or equal to n, and n take I plus 1 is less than m. So as you can see, this condition here is almost exactly the same as the condition we were doing before. We just got these extra terms kicking around. Okay? So once again, I invite you to sort of fill in the gap that you can precondition strengthen from here to here. So I invite you to prove that if you assume this, S equals I plus 1 on 2, and I is less than or equal to n, and I strictly less than n, and n take I is equal to m. If you assume all of this, then you should be able to prove all of that, just by some like tedious algebra. S plus I plus 1 equals I plus 1, I plus 1 plus 1, all on 2, and I plus 1 less than or equal to n, and n take I plus 1 less than m. So prove that just by doing some algebra. Check that it's correct by logic. This is true by assignment. 1, 2, 3, precondition strengthening. Lines 1, lines 2. Assignment. Sequencing by 3 and by 4. And so now I can sort of put the two bits together. So I've got 5. What did we show before? We showed that our choice of variant was a legitimate choice of variant, i.e. that P and B implies E is greater than or equal to 0. Where did I do that? Oh, that was just up here. So really, maybe this is really my line 0, perhaps. So line 0 by logic. Do all the stuff, and then you can combine 0 together with 5 using our new fancy while rule to get P, S equals I plus 1 on 2, and I less than or equal to n, while B, I is strictly less than n, do the code, I is assigned to be I plus 1, S is assigned to be S plus 1, and then post condition P and not B. So S equals I plus 1 on 2, and I is less than or equal to n, and not B. So the negation of I strictly less than n. By while rule total completeness, lines 0 and lines 5. Okay. Now how do I get from line 6 down to what I really wanted? And what is it that I really wanted? I wanted basically this snippet of code up here. It's exactly the same as what we did before, but you just replace the squiggle braces with square braces. So from this point onwards, you just do what we did here from line 8 down by doing precondition strengthening, post-condition weakening. And we know this will work because we're using the same invariant as we were before. So I invite you to fill in the proof, and get your last line at the very bottom should be this whole thing there. So I invite you to finish this off as an exercise. Again, it's basically the same thing as it was before. So that's how we prove this code snippet here using total correctness. So what does it guarantee to me? It guarantees that if this precondition holds, then I guarantee to you the code will terminate, and then also I guarantee to you this post condition will hold. All right? So there we go.